Hey everyone, and welcome to a deep dive into something you see literally every day, layered materials.
Yeah, the things that make up pretty much everything around us.
We've got this fascinating research paper here that dives into the world of computer graphics and how to realistically simulate the look of these layered materials on a computer screen.
It's a challenge that has stumped researchers for a while.
For sure, because simulating light as it interacts with different materials is already hard enough.
Yeah, but when you add layers into the mix, it gets a whole lot more complex.
Okay, so let's break this down for a second.
Yeah.
You've got all these different layers stacked on top of each other, each with their own properties.
Right, each layer might have a different thickness, a different color, even a different way of scattering light.
And as light passes through these layers, it gets reflected, it gets refracted, it gets absorbed. It's like a wild goose chase.
It really is, and the way light interacts with one layer affects how it interacts with the next one. It's all connected.
Exactly.
Yeah.
And that's what makes it so challenging to simulate accurately. Right, because you can't just treat each layer in isolation. You have to consider the entire system as a whole.
It's like trying to bake a cake with a million different ingredients, each one affecting the final taste and texture.
And if you get even one ingredient slightly wrong, the whole thing could fall apart.
Okay, so we've established that simulating layered materials is hard.
Really hard.
But that's what makes this research paper so interesting.
Absolutely. These researchers have come up with a new method that tackles this challenge head on, and the results are pretty amazing.
Okay, so tell me more about this new method.
Well, they call it a position-free approach, which might sound a little intimidating at first.
Position free, huh? I'm intrigued, but I need a little more explanation here.
Sure. So imagine you're shining a flashlight on a wall. The way that light scatters is described by something called a BSDF. But in this case, we're not talking about a single wall. Think of it as a stack of walls, each representing a layer of the material.
Okay, I'm starting to get the picture. So instead of tracking the light as it hits each individual point on the surface, they're focusing on how deep it goes within those layers.
Exactly. They're ignoring the horizontal position of the light and just focusing on the depth. And this is where the position-free part comes in.
So they're simplifying the problem by reducing the number of variables they need to track.
Exactly. And the simplification allows them to create simulations that are not only more accurate, but also much faster.
It's like finding a shortcut through a dense forest instead of having to navigate through every single tree.
Exactly. You get to the destination much faster and with a lot less effort.
And this shortcut leads to some pretty impressive results, right?
Oh, absolutely.
Yeah.
They've managed to simulate those really subtle light interactions that traditional methods really struggle with.
Like that shimmering effect you see on satin fabric, or the way velvet seems to absorb light until you hit it at just the right angle.
Yeah, those are prime examples of something called anisotropic scattering, where the way light scatters depends on the direction it's coming from.
It's those kinds of nuances that really make a material look and feel real.
Absolutely. And this new method is able to capture those nuances with remarkable accuracy.
Now I'm curious to see how this all looks in practice.
Well, luckily, the researchers have included some amazing visuals in their paper. You should definitely check out Figure 2. It's a side-by-side comparison of their method with the standard techniques, and the difference is pretty dramatic.
I bet. So what exactly are we looking for in this figure?
Well, pay attention to the details. Look at how the light interacts with the different materials. See how it captures those subtle variations in color and intensity. That's what sets this method apart.
Okay, I'm definitely going to take a closer look at that figure.
You should. It's really impressive. And it's not just about pretty pictures either. This new method has the potential to revolutionize the way we create and experience virtual materials.
That's what I'm most excited about.
Me too. Think
Yeah.
about the applications in fields like product design, virtual reality, even special effects in movies.
I can see this being used to design everything from cars to clothes to create virtual worlds that are indistinguishable from reality.
Exactly. And it all starts with this new understanding of how to simulate light in layered materials.
It's like they've cracked the code to a whole new level of realism.
They have, and it's really exciting to see what they do with it next.
Okay, so now that we've got a good overview of the method itself, let's dive a little deeper into how it actually works.
Sounds good to me. Let's start with the two ways they approach light simulation: the forward approach and the bidirectional approach.
Oh, those sound intriguing.
They are. And don't worry, we'll break them down in a way that's easy to understand, and we'll even reference those helpful visuals in Figure 7 of the paper to illustrate the concepts.
Excellent. Let's get to it.
All right, so let's talk about these two approaches, the forward and the bidirectional.
Yeah, I'm really curious to hear more about how they actually work.
Well, the forward approach is kind of like traditional path tracing, where you follow the path of a single ray of light as it bounces around.
Ah, path tracing, I've heard of that.
Yeah, it's a classic technique in computer graphics.
So are they just applying path tracing to layered materials?
Well, not exactly. They've added a really clever twist with something called next event estimation.
Next event estimation. Okay, now we're getting into the nitty-gritty.
It's not as complicated as it sounds. Basically, it's like giving those light rays a little boost, a shortcut, if you will.
Okay, I like shortcuts. Tell me more.
So instead of letting the light ray bounce around aimlessly, they use next event estimation to guide it towards the nearest light source.
So they're telling it, hey, there's a light over there, go check it out.
Exactly, and this helps to reduce noise and improve the accuracy of the simulation.
It's like they're giving the light rays a map to follow.
That's a great way to think about it. And they can even combine this next event estimation with traditional path continuation, so they get the best of both worlds.
They're covering all their bases.
Exactly. Now on to the bidirectional approach.
Okay, this one sounds even more intriguing.
It is. It's like they're playing a game of cosmic billiards.
Cosmic billiards. I like the sound of that.
So imagine you're shooting light rays from both the light source and the camera,
Okay, I'm visualizing it.
and then you figure out where those rays intersect within the layers of the material.
So it's like they're meeting in the middle.
Exactly. And the cool thing is that there are multiple ways to connect those paths.
Multiple paths. So it's not just a straight line from the light to the camera.
Right. They have a lot of flexibility in how they approach the problem. And this allows them to handle really complex scenarios like those involving highly anisotropic materials.
Which is something that traditional methods really struggle with.
Right. Those materials where the way light scatters depends on the angle you're looking from.
So the bidirectional approach is like a secret weapon for those tricky cases.
You could say that. And the best part is that it's surprisingly efficient.
Efficient so it doesn't require a ton of computing power.
Not as much as you might think, which makes it really practical for real-world applications.
Okay, so we've got the forward approach and the bidirectional approach, both pretty impressive.
Yeah, they each have their own strengths and weaknesses, and the researchers have done a great job of explaining when to use each one.
Now, there's one thing I'm a little confused about. They mentioned something called PDF estimation.
Yes, the probability density function. That's a crucial part of any Monte Carlo simulation.
I'm familiar with Monte Carlo simulations, but I'm not sure I understand how PDFs come into play here.
Well, basically, they need these PDFs to make sure that their multiple importance sampling works correctly.
Multiple importance sampling, another fancy term.
It's basically a way of combining different sampling techniques to get the most accurate results.
Okay, I see. So the PDFs are like the glue that holds everything together.
That's a good way to think about it. And the tricky thing with layered BSDFs is that you can't just calculate those PDFs directly.
So they had to come up with a workaround.
Exactly. They developed two new methods for estimating those PDFs.
Right.
One that's really accurate but slow, and one that's fast but approximate.
So it's a trade-off between speed and accuracy.
Exactly. And they've shown that the approximate method works really well in practice.
So they found a sweet spot.
They have.
Yeah.
And it's just another example of their ingenuity in tackling this challenge.
Okay, so they've got these clever techniques for simulating light transport, but how do they actually apply them to real-world materials?
Well, they've demonstrated their method on a variety of different materials, including fabrics, metals, and even multi-layered materials like a kettle with water inside.
A kettle with water, that's pretty ambitious.
It is, and the results are amazing. They're able to capture all those subtle details that made the materials look so realistic.
Okay, so now I'm really eager to see what this method can do. Let's dive into those specific examples.
Sounds good to me. Let's start with fabrics, shall we?
Absolutely. Fabrics are always a challenge in computer graphics, so I'm curious to see how they tackled that. Okay, so fabric, huh? It's one of those things that's notoriously hard to get right in computer graphics.
Oh yeah, fabric simulations have always been a bit of a holy grail.
It's because there's just so much complexity going on at the microscopic level, all those tiny fibers and how they interact with light.
Exactly, and not all fabrics are created equal.
Yeah.
You've got everything from smooth satin to fuzzy velvet, each with its own unique way of scattering light.
And that's where this new method really shines, right?
It does. They've managed to capture those subtle details that make fabrics look and feel so real, like the way satin shimmers or how velvet seems to absorb light except at certain angles.
It's like they've unlocked the secret to virtual fashion.
In a way, they have. And it's not just about making pretty pictures either. This has real-world applications in fields like textile design and virtual clothing try-ons.
I can imagine designers using this to create and test new fabrics without having to actually manufacture them.
Exactly. And consumers could try on clothes virtually and see how they look and drape on their bodies.
Okay, so let's get specific. What kind of fabrics did they actually simulate?
Well, they've got some great examples in their paper. Figure 13 shows some really impressive renderings of satin twill and even velvet.
Velvet, that's a tough one.
Oh yeah, velvet is notorious for being difficult to simulate realistically because of the way it absorbs light.
It's like it only reveals its true color when you hit it at just the right angle.
Exactly. And their method is able to capture that effect beautifully.
Now, I'm curious how they actually created these simulations. Did they just rely on algorithms?
Well, algorithms are definitely part of it, but they also used real-world data to inform their simulations.
Real-world data, like what?
They actually use micro-CT scans of real fabric samples.
Wow, so they're not just making stuff up, they're actually basing their simulations on the physical structure of fabrics.
Exactly. And that attention to detail really pays off in the final results.
I can imagine those micro CT scans provide a wealth of information about the arrangement of fibers and how they scatter light.
Absolutely. And it's that level of detail that allows them to create such realistic simulations.
So they've got the algorithms and the real-world data. What else?
Well, they also developed a really clever way of handling the normal mapping issue.
Normal mapping? Remind me what that is again.
It's basically a technique for adding surface detail to 3D models without having to actually model all the tiny bumps and grooves.
So it's like a shortcut for creating realistic textures.
Exactly, and it's a really common technique in computer graphics.
But it can cause problems with layered materials, right?
It can because normal mapping essentially alters the way light interacts with the surface, and that can mess with the calculations for layered materials.
So they had to find a way to reconcile normal mapping with their new method.
They did.
Hmm.
And they came up with a really elegant solution that preserves the accuracy of the simulations while still allowing for the use of normal mapping.
That's impressive. It's like they found a way to have their cake and eat it too.
They have. And it's a testament to their deep understanding of both the physics of light and the intricacies of computer graphics.
Okay, so we've talked a lot about fabrics. What other materials did they test their method on?
Well, they also showcase some really cool examples of multi-layered materials like a kettle with a transparent water layer.
A kettle with water now that's getting fancy.
It is, and they didn't just stop there. They also simulated a translucent coating layer and even a combination of both.
So they're really pushing the boundaries of what's possible with layered material simulations.
They are, and the results speak for themselves. Those kettle renderings are incredibly realistic. You can see how each layer affects the way light passes through the material.
It's like you could reach out and touch the virtual kettle and feel the different layers.
Exactly, and that's what's so exciting about this research. It's not just about making pretty pictures. It's about creating virtual experiences that are indistinguishable from reality.
And that opens up a whole world of possibilities for fields like product design, virtual reality, and even scientific visualization.
Absolutely. This method has the potential to revolutionize the way we create and interact with virtual objects and environments.
Well, we've covered a lot of ground today. We've explored the intricacies of layered materials, learned about this groundbreaking new method for simulating their appearance, and even seen some amazing examples of what it can do.
It's been a fascinating journey, and it's clear that this research has the potential to change the way we think about and create virtual materials.
Absolutely, and I'm sure this is just the beginning. We're going to see even more amazing applications of this technology in the years to come.
I completely agree. This research is a testament to the power of human ingenuity and the ever-evolving world of computer graphics.
Well said. And to all our listeners out there, we encourage you to dive into the source material yourselves and see what insights you can uncover.
There's a whole world of fascinating details waiting to be explored.
Until next time, keep exploring and keep wondering.
And keep pushing the boundaries of what's possible.
Yeah.